Okay, so we will start now. So this is lecture number 3, as you know, and again we are with the module number 1, that is review of MOSFET operation and its fabrication. So today, what we are going to learn, we are going to learn about uh, short channel effects. So you will know what is meant by short channel effect. Okay, so then let us see what we have studied in our lecture number 1 and lecture number 2. So in lecture number 1, we have studied MOSFET operation. You know that MOSFET is metal oxide field effect transistor, and it operates in 3 regions. One is cutoff region, in which drain current is 0. Then linear region. In linear region, drain current is linear function of drain to source voltage. Okay. And in saturation region, third region of operation is in saturation region, drain current is constant and it is independent of drain to source voltage. Yeah. In cutoff region, gate to source voltage is less than threshold voltage. In linear region, gate to source voltage is greater than VT, but drain to source voltage is VGS minus VT. That is the condition. And in saturation region, again gate to source voltage is greater than VT, and drain to source voltage is also greater than VGS minus VT. Then we have seen MOSFET equations, and then in last lecture we have seen MOSFET capacitances. So there are various MOSFET capacitances. Then in lecture number 2 we have started with MOSFET scaling, because we have very desktop, we have laptop, we have cell phones, we have so many small gadgets, electronic gadgets, whose computational power is very high as compared to first generation computer, and this has happened because of the MOSFET scaling. So there are two types of scalings. One is called as constant field scaling, and other is called as constant full scaling, is also called as full scaling. Full scaling, why it is? Because we scale voltages as well as dimensions. So that's the reason. Yeah, yeah. And then there is another type of scaling that is called as constant voltage. So that is partial scaling also, because we are just scaling dimensions and we are not scaling any voltages. Yeah, voltage dimension. So this yesterday, 2 lectures we have seen. Now, what is objective of this lecture? Objective means to describe what I will do, to describe various short channel effects in scaled MOSFET. Scaled MOSFET means small MOSFET, miniaturized MOSFET. So there are effects, because you know that yesterday I have just described you, explained you what are the advantages of MOSFET scaling. What are the advantages? Basically, we are getting high performance. Then in a small, yeah, yes, less voltage. Yes, power consumption is less, space is less. Yeah, yeah. But advantages will not come in free. So you need to pay something for that. So that is called as short channel effects. So today we are going to learn about it. So students will be able to describe various short channel effects present in short channel MOSFET. One is called as long channel MOSFET and another is called as short channel MOSFET. So let us understand what is it all about. So see here, what is mean by short channel effect or short channel device. So basically, if length of the channel, so I will just draw here for your understanding purpose. So this is the MOSFET. Can you see here something? Length. This is N plus region. This is also N plus region. You can see that. And this is called as channel length, right? This is called as channel length. But you know that this is basically p-type substrate. So you know that this is p-type substrate. In p-type substrate, this is n plus drain, n plus source, and therefore whenever there is a p-n junction, there is a depletion region associated with it. You might be knowing. So this is the depletion region. So this is the depletion region associated with it. Yes, this is the depletion region associated with it. So if you see, so it says that if length of the channel is of the order of width of the depletion region of source and drain junction, then MOSFET is called as short channel MOSFET. Now see, this is the width of the depletion region. Here, can you see this depletion width? Can you see depletion width? So tell me that depletion width is smaller or larger here? It's very small, because L is very large. Can you see L is very large? Yeah, that's why this such type of transistor you cannot call as short channel transistor or MOSFET, but it is long channel. So let us see now what is short channel MOSFET. So I will draw the picture again of short channel MOSFET. Now here, so this is again n plus region, and here it is n plus region, and this is substrate. This is p-type substrate, right? Now again here also there is a depletion region. So where will be the depletion region? Depletion region will be here, like this, and there will be depletion region. And if I draw here length of the transistor, so length of the transistor, if I want to show, then length of the transistor here is from this point to this point. Now can you see that length of the transistor and width of the junction is approximately same? Huh? It's approximately same. You can see that. You can observe that. So such type of MOSFET is called as short channel MOSFET. Understood what is meant by short channel MOSFET? Yeah. So you have understood what is short channel MOSFET. So if length of the channel is of the order of width of the depletion region of source and drain junction, then such MOSFET is called as short channel MOSFET. Or if length of the channel is of the order of junction depth of source and drain, then resulting MOSFET is known as short channel MOSFET. So that is definition is one and same. Now, because of short channel, there are various effects. Okay. So what yesterday we have seen that there was a MOSFET equation, and in MOSFET equation, you know that in MOSFET equation, if you remember, this I, yes, I was proportional to what? 1 by L. Yes, means if I reduce L, then what will happen to the I? I will increase. But can I reduce this I for a longer time? No, yesterday we have seen that it was 10 nanometer. 10 nanometer. How long I can decrease this? No, I cannot decrease to very short length, because various effects will come in pictures, and these are called as short channel effects, and one is called as velocity saturation. So you will understand what is meant by velocity saturation. Then second is called as mobility degradation. Velocity saturation, mobility degradation, then threshold voltage roll off. Okay, then drain induced barrier lowering. These are the effects, and we will learn what are these effects. Then hot carrier effects and tunneling currents. Okay, so what are the different effects now? One is velocity saturation, then mobility degradation, then threshold voltage roll off, and then hot carrier effects and tunneling currents. So these are called as short channel effects, and these effects are there only in short channel MOSFET. Okay, only in short channel MOSFET. So let us see one by one what are these effects. Okay, so first effect is velocity saturation. First effect is velocity saturation. So let us understand what is meant by velocity saturation effect. Okay, so velocity saturation effect, basically what happens, you might be knowing, as you keep decreasing in constant voltage scaling. What happens in constant voltage scaling? In constant voltage scaling, you know that electric field is given by V by L. Yes, as we keep on decreasing L, your electric field increases because voltage is constant. Because this is constant, right? This is constant. So therefore, what happens as electric field increases, so your velocity of electron is proportional to electric field. You know why current flowing through MOSFET increases in linear region? Because velocity of charge particle increases, that is electron increases, electric field increases, velocity increases, but that velocity will not increase indefinitely. It will not increase independently. Suppose my electric field is infinity, uh, will there be infinite speed of electrons? Huh? It will not increase because it will saturate. Why it will saturate? Saturate because see what is the maximum speed here? Maximum speed is speed of light. So you cannot go beyond that speed of light. So there is a saturation of each and everything. So therefore, as shown in this curve, you can see in this curve basically. Here, as shown in this curve, you can see as electric field is as electric field increases, your drift velocity on x-axis, you can see your drift velocity or velocity of electron increases, but it will increase only up to certain point here. Can you see this? After that, it saturates. It saturates. Therefore, once saturation happens, electron this will not increase. Speed of electron will not increase. Okay, and therefore this current becomes constant. It will not increase. Means even if you decrease L, even if you decrease L, you will not get any increase in current. Why? Because of saturation. This one. Because of the saturation current, you will not get any increase in the current. Okay, so this effect is called as saturation current effect. Okay, this effect is called as saturation current. Now here it is shown. If you see this curve, see actually if device is long channel device, means if there is no short channel effect, your current is this much high current. Can you see here? But due to saturation, even if device is this one, your current is very small. Actual current is this much, and this is the predicted current, and this is because of velocity saturation. Okay, now next effect is mobility degradation. Okay, what is mean by mobility degradation? Mobility degradation means, you know that in current equation yesterday you have seen that current I, yes, it is given by which equation I am writing here. I is proportional to, I will write, not write any everything, proportional to mobility mu n. Yes, current is proportional to mobility, and when we scale MOSFET we consider that there is no change in mobility remains same. But this is not the case. What is the reason? The reason I will tell you. I will draw MOSFET here again. This is n plus, this is n plus, this is oxide thickness. Okay, and on oxide thickness there is a metal. We apply here voltage, gate voltage V, and there is this is the structure of MOSFET basically. This is drain, this is source. So when voltage is kept constant and channel length is reduced and oxide thickness is also reduced, electric field will increase. As you know that electric field will increase, electric field. And since electric field increases, here are some electrons, here are some electrons. They will just, because of the high electric field, they will strike this oxide. Okay, and when they strike the oxide, scattering of electron will happen. Scattering means they will scatter from the oxide, and when they scatter basically they lose their velocity, they lose their mobility because of high electric field. As I mentioned here, in short channel MOSFET, lateral electric field as well as vertical electric field increases because of scaling. Increased vertical field, so this is vertical field, this is lateral field. Increased vertical field causes scattering of charge carriers at silicon dioxide interface. So this is the interface. Scattering of charge carriers results in degradation of mobility. And if mobility degrades, then what will happen? Current will become less. Yes, because if mobility degrades, current will become less. Yeah, so current will become less. And therefore, this effect is called as mobility degradation. Now, this is explained, same thing is explained with the help of equation. So, this is effective mobility of charged particle. So, whatever you see here, effective mobility, and it is given by, this is nothing but uh, mobility without any electric field, mu n 0. Yeah. Then it is given by mu n 0 divided by 1 plus n VGS minus VT. So, if you increase VGS, then this particular factor will increase, right? And that factor is coming in denominator. So what will happen? Effective mobility will decrease. So mobility is inversely proportional to vertical electric field, and therefore in short channel MOSFET, drain current reduces because of mobility degradation. So although we say that drain current increases, but because of mobility degradation due to scaling, MOSFET drain current will decrease. So this is also called as short channel effect. Okay, then there is called as depletion. Another effect is called as threshold roll off. So what is threshold roll off? Threshold roll off means actually when we reduce the channel length, when we reduce the channel length, okay, This is threshold voltage. Actually, threshold voltage should be constant and it should be independent of channel length. Okay, it should be independent of channel length. But actually what happens, because of this voltage, threshold voltage roll up, as we decrease channel length, so threshold voltage reduces. So this reduction in threshold voltage is called as threshold voltage roll off. Now why it is so? Because if you see here, this is the depletion region. Okay, so depletion, width of the depletion region is very small as compared to channel region. Can you see here? Channel region is very high. But in short channel MOSFET, so this is your depletion region. This is your depletion region, this much. This much is your depletion region. And what is the channel? Channel is also of the order of the same. So therefore this depletion charge plays very important role in deciding the threshold voltage. So that will be clear from next slide. Okay, now see here. So threshold voltage is basically given by this equation. So don't this one, just understand. So whatever is QB0, QB0 is channel charge. Okay, QB0 is channel charge. So this channel charge is very large in short channel MOSFET, and here depletion charge is not considered. So depletion charge becomes channel charge, and that's the reason this, as you keep on decreasing your channel length, see channel length, so your threshold voltage also reduces. Okay, so this type of effect is called as threshold roll off. Okay, so then there is another effect that is called as drain induced barrier lowering. So what is meant by drain induced barrier lowering? So for that you consider, and this effect occurs only in short channel MOSFET. Here you can see this is long channel MOSFET. Here is source. Can you see? Here is source. Here is drain. Now what happens when we apply, means suppose gate voltage is 0, source is also 0, this MOSFET is off because gate voltage is 0. When MOSFET is off, so what we expect, when MOSFET is off, we expect that drain current should be 0. Yeah, because these electrons in source cannot enter into channel region. Why? Because this is the source. If you see this diagram, this is the source, and they see this barrier here, because there is a barrier for electrons to enter into channel region. If these electrons want to enter into channel region, they have to overcome this barrier. Okay, they have to overcome this barrier, this much barrier. So this is the barrier from this point to this point, this is the barrier. Yeah, but when we apply, because drain and source are far away from each other, but when you increase short channel MOSFET, drain and source are close to each other, right? So yeah, as you are increasing drain to source voltage, there is a barrier, this barrier, electric field, and this electric field will lower the barrier at source. Can you see there is a lowering the barrier, and that's why due to lowered bias, now electron can easily enter into channel region, and they constitute this one. Means this is called as leakage current. Actually we don't want this current. This is called as leakage current. Means even if gate voltage to the MOSFET is 0, but due to this drain induced barrier lowering, drain induced means this drain will lower the barrier at source. It will lower the barrier at source, and that's the reason some of the electrons will get energy to enter into channel region. They enter into the channel region and they constitute current. That current is called as leakage current or subthreshold current. Okay, that current is called as subthreshold current. Okay, so here here you can see this is the difference. So this is basically gate voltage. You can see x-axis is gate voltage here and y-axis is drain current, and this is due to debulk basically. Means if I increase drain to source voltage, when drain to source voltage is 0, my drain current, leakage current is this much. Leakage current means when gate to source voltage is 0, this much. But when I increase drain to source voltage, even gate voltage is 0, my drain current increases to this value. So this is due to the debulk effect or drain to this one. So this current is also called as subthreshold leakage current, and leakage current we don't want, as it causes the power dissipation. Okay, how to there are various ways to do that, so that we will see afterwards how that is. Okay, then next effect is called as hot carrier effect. Now what is meant by hot carrier effect? Okay, so hot carrier effect is basically, can you see here? So as you know that we increase this one in constant voltage scaling. What happened? In constant voltage scaling, electric field is given by V by L, and constant voltage is constant while this is reduced. Yes, L is reduced. So therefore electric field will increase. So when electric field increases, these electrons, these are the electrons basically, these electrons will gain very high velocity. Yes, as electric field increases, their velocity of charged particle increases, and if velocity increases, kinetic energy of charged particle increases. Do you know kinetic energy? Kinetic energy is given by half mv square, where m is mass and v is velocity. If velocity increases due to increase in electric field, their kinetic energy increases. So as kinetic energy of charged particle increases, and as they starts moving from source to drain, at source there is a very high electric field. So therefore what will happen? They will strike the oxide. And as they strike the oxide, these are hot electrons, their energy is very high, they penetrate into oxide. These electrons will penetrate into the oxide, they will damage the oxide at drain side, and as they damage the oxide drain side, their threshold voltage of the MOSFET increases. And you know that as threshold voltage also of MOSFET increases, because drain current is proportional to, if threshold voltage is less, drain current is more. Okay, so therefore drain current decreases. If drain current decreases, then speed and everything decreases. You might have seen laptop. So when it's new, its speed is very good, right? But as you use that laptop for 3-4 years or 5 years, then its speed reduces, means its performance degrades. So what is the reason? The reason is that its speed reduces because of this such kind of effects. This is hot carrier effects, because chips, that processor speed reduces, because transistors used in that processor undergo such type of effect, that is hot carrier effect, and their threshold voltage gradually increases. Gradually means over the years, instantly it doesn't increase, and that's the reason you cannot see the change in speed of laptop instantly, but over the years you can observe that. Okay, and one of the reasons for this is hot carrier effect. And hot carrier effect, why? Because as you scale the MOSFET, electric field increases. Because of the increased electric field, velocity of charged particle increases, kinetic energy increases, and when such kinetic energy, a high kinetic energy electrons are called as hot electrons. When they come near drain, they strike the drain region, they penetrate into the drain, and they damage the oxide. And because of this damaged oxide, uh, threshold voltage of MOSFET increases gradually. Such type of effect is called as hot carrier effect. Okay. Okay, so here you can see the effect of hot carrier effect carriers. Now here you can see here what is that dotted. Basically, this is whatever is this continuous line. This is without hot carrier effect, and if there is a hot carrier effect, then you can see that this current is reduced. Okay, so this is called as hot carrier effect. Okay, then next is tunneling currents. What is meant by tunnel current? So see here, along with MOSFET channel length, we scale oxide thickness. This is oxide thickness of MOSFET, vertical dimension. Okay, we scale oxide thickness. So when you scale oxide thickness is oxide is basically insulator. Okay, but when you scale, so what happens? This becomes very very thin, and when it becomes very thin, because of some quantum mechanical property, actually why oxide is insulator, because electrons, if you want conduction, this electron has to cross this barrier like this, and it's very difficult to apply such a high voltage. Okay, that's why in normal operation this oxide don't conduct any current, so that's why it's insulator, because it is thick also. But when you scale oxide, it becomes thinner, and because of this thin, because of quantum mechanics, there are energy states available, and they tunnel through such energy states, so they don't need to cross the barrier, so they tunnel, and this tunneling electron constitutes some current, so that is called as tunnel current. Actually oxide is insulator, we want oxide to be insulator, but as you scale MOSFET, it becomes thinner, and through such thin, yeah, yeah, it passed through like this tunnel. Can you see? Yeah, can you see here tunnel? There are many tunnels on Mumbai Pune expressway, so vehicle don't have to overcome that barrier, but they can easily tunnel through this one, because that is created. So here also such tunnels are created automatically because of quantum mechanical effect, when this oxide thickness is very thin, right? But in long, if it is thick, then there is no conduction. So this effect is because of MOSFET scaling, and this is called as tunneling currents. Okay, yeah. So these are all short channel effects. Okay, okay. Now again we will see other things that are, these were short channel effects. Now what you are going to learn is second order effect. So what is meant by second order effect? Okay, so you will know what is meant by second order effects in MOSFET. Then this we are not going to learn today, layout and this one, that is for next lecture. Okay, so after successful completion, you will know what is meant by second order effects in MOSFET, and to know what is its impact on MOSFET operation. So there are three types of three second order effect. One is called as channel length modulation, body bias effect, and subthreshold leakage. So out of these three, we have yesterday learned this channel length modulation. You know what is meant by channel length modulation? Yeah. So channel length modulation is basically as you increase drain to source voltage, right? So this pinch off point, so here it is called as pinch off point, that point moves towards the source as you keep on increasing this one. So therefore effective channel length, so this L is the effective channel length, but it delta L increases, so therefore effective channel length reduces. So this you need to take into account, so therefore this factor is added, right? So this factor is added. So you can see here, so dash dash is without channel length modulation, and whatever you see thick characteristic, that is with channel length. So current is increasing as you increase your VDS. So this effect is called as channel length modulation, right? Now similarly, up till now we have seen that substrate is connected to ground. There are four terminals. Substrate is connected to ground. So therefore, but when substrate is not connected to ground, it is connected to negative highest potential. And because of that, what happens? Threshold voltage of MOSFET increases. So this is the equation. So VTHO or VTO is threshold voltage without bias voltage. That is substrate voltage. But when there is a substrate voltage, its threshold voltage increases. And that's why effect of this effect is called as body bias effect. Okay. And it is taken into account by this gamma factor. Channel length modulation is taken into account by lambda. Okay. So what is body bias effect? When substrate voltage is connected to non-zero voltage, non-zero potential, then threshold voltage of MOSFET increases, and that effect is called as body bias effect. And as threshold voltage of MOSFET increases, drain current of MOSFET decreases for given gate to source voltage. Then there is another effect. So see here, this is body bias effect. So this is Vx, which is substrate voltage. So when substrate voltage is zero, your drain current is very high. But as you keep on increasing your substrate voltage in negative direction, that is Vx, drain current reduces. So this is body bias effect. And gate to source voltage is constant. Now, as I mentioned, when VGS is less than threshold voltage, means when gate to source voltage is less than threshold voltage, we consider MOSFET is off. And when MOSFET is off, we consider that, what we consider? We consider that IDS is zero. But actually that doesn't happen. There is small current even if threshold gate to source voltage is less than threshold voltage, and that current is called as sub-threshold leakage current or sub-threshold conduction, and it is given by this equation. Okay, so these are basically second order effect. One is channel length modulation, body bias effect, and sub-threshold conduction. And this ends the lecture number. This is end of lecture number 3. You have any questions to ask? So what we have studied today? We have studied, just I will, so short channel effects. What are the short channel effects? Well, these are the short channel effects, and we have seen what is their impact on the performance, mobility degradation, threshold voltage roll off, then drain induced barrier lowering, then this is impact of drain induced barrier lowering, sub-threshold leakage current, then hot carrier effect we have studied. Then we have also studied tunneling currents. Then we have studied channel length modulation, second order effect. Then we have studied body bias effect. Okay, so these are the things we have done, sub-threshold leakage and sub-threshold leakage. Okay, so here now we will stop, and in next week we will continue our DVLSI. Okay. Can we stop here? Okay, bye. Good day. Yeah.